Today we are looking at the relationship between kinematics, rotational kinematics of something rotating, and the linear kinematics of a particle which is also engaged in some kind of rotation. So in other words, how can one bug be going faster than another if they're both going at the same speed? That's meant to be intriguing. And in fact, this topic made me think of a Calvin and Hobbes cartoon that I saw 20 years ago. You might not even know Calvin and Hobbes, so old that it is. And it's either encouraging or discouraging. I'm not sure that I could find this on the internet in like 3 mouse clicks. And so I'll let you pause and read it. So we're back. So the point is that, the two different points on a rigid rotating object are both rotating together in the sense that they both have the same angular velocity. So when Calvin's dad talks about the different speeds of the 2 points, he's saying that the 2 points on the record on one disk have different linear velocities, v, that are going different numbers of meters per second, but they both make the same revolutions per minute. They both have the same angular velocity. And so how is that possible? Well, it's possible because it is. So let's see how and why. Let's take a look at our, speaking of bugs, let's take a look at our bugs on this rotating turntable. And the other day we looked at these and we just saw one bug rotating. They give me 2, I will use 2. I'm going to put a second bug on this turntable. And the reason I do that is basically to point out the Hobbesian illustration that when these things are rotating, they're both undergoing the same number of revolutions per minute, or in other words, they both have the same angular velocity. And I remind us that we have been looking at rigid rotating objects. I'm going to let them rotate, and I'm going to just mention briefly rigid rotating objects, meaning that they don't get all smeared. What? They're not made out of something not rigid, oatmeal. So we would not have a rotating glob of oatmeal because bits of it can rotate differently from others. The sun is one example of a rotating object that's not rigid, and different points on the sun go around in more or fewer days than other points on the sun because it's this big ball of plasma gas or something stupid like that. In any event, if you have a rigid rotating object, this is where the rotational kinematics is very handy because every point on this disk has the same angular velocity, the same omega. But you might recognize that these 2 bugs are going at different numbers of meters per second because the beetle, I'm going to pause this. I think I'm going to pause this. I'm going to pause this. I'm going to try to pause this. There. The ladybug beetle goes around this size of a circle in the same amount of time that the green beetle thing goes around a circle this big, clearly covering more distance in the same amount of time. So the green beetle has a greater linear velocity than the ladybug beetle. This is illustrated in this cute little simulation because I can add velocity vectors. Let me get these guys going again. I can add velocity vectors. And you can see, let's get them going a little faster. Okay, there we go. And you can see here that the green beetle, if I pause this, the green beetle has a larger velocity vector than the ladybug beetle because it's going faster. It's going more meters per second. Okay, how do the equations and stuff work out? Let's take a look. So let's consider for now a rigid rotating object. So I will draw this circle thing, and this could be a turntable or a planet or something like that. But I'm going to say that I'm looking down on its rotation. And so the axis of rotation is in the middle, and for the sake of argument, it's rotating counterclockwise. So it has a positive angular velocity. And I'm going to say, let's consider a point P on this rigid rotating object. And as this thing rotates, P travels. P is right now located along a reference line. This, of course, is the positive x direction. And so P is at the origin in terms of its angular position. it right now has a value of theta equal to 0. Then as this thing rotates, there's no way I'm going to be able to simulate the rotation. Oh, look at that. Okay, so as P rotates, then it now has a new angular position. So I'll draw a new reference line. It has traveled through this angle theta. And point P has, in so doing, what I want to do is I want to relate how far it's traveled in terms of its angular position and how far it's traveled in terms of distance. So I'm also going to mark an arc here. This is getting a little bit cluttered. The actual letter P in pieces. Oh, pieces. Pieces of P's. Put things back. Thank you. All right, so this green line here is the arc length, which I'll label S. And point P has traveled that distance, S, away from its original point. And it has also traveled through an angle theta. And how are these things related to each other? No surprises here. If I also mark the distance that point P is from the axis of rotation, I'm going to mark this distance, and I'm going to call distance the little letter r. Now, I want to make a distinction between this little distance r, which is the distance that P is from the axis of rotation, and the radius of this actual disk, which I will mark here with a large capital R, and that is the radius of this rigid rotating object. Point P is a distance little r away from the center. And I really want to make the distinction because I'm going to be using big R and little r in different ways. So please be careful in these notations. All right. Okay, so if I look at point P, how are its distance from the axis, little r, the arc length has traveled s, and the angular position it has now, theta, little tiny theta, and how are they related? Again, no surprises here. Theta is defined as arc length over radius. Remember that we're always measuring theta in radians, which is a ratio of two different distances, s over r in this case. And so we're measuring in radians. Good for us. Okay, let me take this definition of theta and rearrange it by multiplying both sides by r, because I can, and that gives me s equals theta times r. All right. What do I want to do with this? I can look at it and admire it, or I can differentiate both sides with respect to time. That sounds like fun, so let's do it. Let's see, I get on the left ds dt. On the right, I get d product theta r dt. What do I have? Well, on the left-hand side, I have ds dt. That is the rate at which s changes, the rate at which the arc length is changing. That's the speed of point P, because it's traveling along this arc, so s marks how far it's traveled. ds dt is the magnitude of its speed. On the right-hand side, point P is always a distance little r from the center, so little r is a constant. I can pull that out, and I get r d theta dt. D theta dt is the definition of angular velocity. So I have v equals r omega. And that is a relationship between your linear speed and the angular velocity, the disk that you're on, and your radius from the center. What this tells us is that for two different points, let's say point P and point, plumbing crazy, point Q, if I put point Q, well-calibrated board, okay, big point Q, farther away, Q is at a larger little r, that's little r, than point P is. And so when Q travels, it's going to travel through a larger arc to here. This is a new location of point Q. They're both traveling, both P and Q are traveling through the same angle every second, but Q travels a longer distance. Q's S, too bad I made P's S green. Q's S is a larger value than the S, the arc length for P, and that's because Q is traveling faster. So, I'm just babbling now, just showing how this equation makes sense. The greater, again, for two different points on the same rigid rotating object, they both have the same omega. that's the reason that we're analyzing these kinematic values in rotation. And that's the reason we invented omega. So 2 points on the same disk have the same omega. Therefore, the one with the larger r has the larger speed, v, which is why Calvin's dad made this very perceptive observation. The farther away you are from the center, the greater your speed. Let's see how that looks with the bugs we have down here. Sure enough, they show me, and I'm sure that this computer simulation is completely accurate, they show me that the speed v is a longer vector for the bug that's farther away from the center, and so that's because when they're both moving, the green bug is traveling faster than the red bug. And in fact, there's a linear proportion. If the green bug is 3 times as far away from the axis as the red bug, is traveling at 3 times the speed. Okie doke. But wait, there's more. Because we can not only relate the linear speed of different points on this rigid rotating object, we can also relate, say, something about accelerations. So let's do that. Okay, we've got this v equals r omega, just writing this again. And, well, I differentiated once with respect to time. What's to stop me from doing it again? Nothing is going to stop me. I'm doing it now. What do I get? Well, on the left-hand side, I'm not going to write it in so many steps this time. dv dt, that's a. On the right-hand side, r is still a constant. I have r times d omega dt. That is r times alpha, which is the angular acceleration. So this tells us that the acceleration is greater the greater your distance from the center, and it's equal to r times your angular acceleration. Here we have to be careful, because in fact, I'm going to show you a conundrum. This says that you only have a linear acceleration measured in meter per second squared if you have an angular acceleration. Having an angular acceleration means that you're rotating faster and faster or slower and slower. If I look back at this record player, I have this simulation going so that the record player is turning at a constant rate, a constant angular velocity. So what's the angular acceleration of this record player right now? Ponder, 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 ponder. It's 0. The angular acceleration, alpha, is equal to 0 for this record player because omega is constant. Well, according to the equation that we just derived, if alpha is 0, then your acceleration is 0. A is 0 if alpha is 0. And as we've just seen, this thing has no alpha, it has no angular acceleration. Does that mean that these bugs have no acceleration? Of course they have acceleration. I know that because if I show acceleration vector on this neat simulation, I get these vectors pointing toward the center. And I also know that if you're traveling in a circular path at a constant speed, you're accelerating toward the center. We call that centripetal acceleration. So what's the deal? Let me go back to this equation that we just derived. We have to be very clear what these A's and stuff mean. This A right here is linear acceleration. What about this A? This A is linear acceleration, meaning it's measured in meters per second squared. But this is not centripetal acceleration. Okay, centripetal acceleration answers the question, is the direction of your velocity changing? And in this case, the answer is yes, it is changing. And these bugs in the simulation, there they are, have a centripetal acceleration. What they don't have is an acceleration that answers a different question. And the question, please, the question that this A answers that we just derived, and we're about to give it a new name, or an old new name, this actually answers the question, are you moving faster or slower? Meaning, what this acceleration is describing what's happening to the magnitude of your speed, the magnitude of your velocity. Are you going faster and faster or slower and slower? And the answer in the case of the bugs is no, you're not. These bugs have a constant magnitude of v. Those green arrows are not changing length. So they don't have any of this kind, going back, they don't have any of this kind of acceleration. Okay, what is this kind of acceleration? This is where we're going to have to be very clear with names of things. This we're going to call a sub t for tangential acceleration. So this A that we just derived, I have enough arrows there almost, stands for tangential acceleration. That refers to its direction. It is a linear acceleration, yes. It is measured in meters per second squared, yes. And its direction is tangent to the circle, which means that if in fact you are traveling in a circular path, I'm going to draw a new, I'm going to get mad at this board, I'm going to calibrate it. Pause. Okay, so I'm going to draw a new rigid rotating object, and with a reference line, and they're not stuck. So I'm going to join them together and group them. Group. Okay, so if this thing is rotating at a constant angular velocity, which pretty much is now, then if I examine a point on this rigid rotating object, remember, do keep in mind, please, that when we're talking about the angular velocity and angular acceleration, omega and alpha refer to the disk. Any point on the disk. The whole disk has a given angular velocity or an angular acceleration. When we refer to v and tangential acceleration, and even centripetal, we'll be getting to in a second, these refer to a point on the disk. So I would say, I will not say what is the linear velocity of this disk, or what is the tangential acceleration of this disk, because different points have different values. So if I choose a point P, if this thing is, I'm going to join it up, a little more grouping. If this thing is rotating at a constant angular velocity, like that, then in terms of linear quantities, so I've frozen this in time, but in fact this thing is moving right now. In terms of linear velocities, it has a certain v, and point P has a certain acceleration toward the center, centripetal acceleration. Okay, but it has no tangential acceleration. AT is 0 if alpha is equal to 0, if you're not rotating faster and faster or slower and slower. If, on the other hand, let me get rid of these vectors for the moment. If, on the other hand, this thing is going around faster and faster and faster and faster and faster. Okay, so if I freeze that as it's spinning faster and faster, then tell me about point P. Well, first of all, does it have a linear velocity? Yes. Tangent to the circle it's traveling in, or perpendicular to a radius. So I'm going to attempt to put a velocity vector in a reasonably accurate direction there. This is where I see the radius. Well, I'll get to It's just the right direction. Does it have a centripetal acceleration? Yes, it does. Okay, that's toward the center of the circle. And in this case, because this disk is rotating faster and faster and faster, it also has a tangential acceleration, which is equal to alpha times r, the tangential acceleration. So we have to keep the acceleration straight. Tangential acceleration measured in meter per second squared. That is what you have if you're rotating a point on an object rotating faster and faster or slower and slower. Centripetal acceleration, this, by the way, is still v squared over r, same as it always has been. I'll be saying a little bit more about that in a second. And that is true, you have that as long as you are moving in a circular path. So let me just say a little something about centripetal acceleration. AC is v squared over r. We've derived that in the past. It's still true. This is, as long as you have a v and you're an r away from the center, your AC is v squared over r. Sometimes it's useful, though, to look at this from the viewpoint of the quantities from rotational kinematics. So I'm going to do a quick substitution. I remember from above that V is omega times R. And so if I sub in omega R for V, I get omega R quantity squared over R, and that gives me omega squared R squared divided by R, which of course is equal to omega squared times R. Okie doke. So we have two different ways we can express centripetal acceleration. This is nothing new. I'm going to write them both in the same place here. A is C is V squared over R, or I can write omega squared times R. These are just different ways of writing the same thing, and those are both centripetal acceleration. Just to summarize our accelerations, we also have a new expression for tangential acceleration, alpha times R. That, again, you only have if you're rotating faster and faster or slower and slower. Just to try to confuse issues as much as possible, we will sometimes find ourselves using a different term for centripetal acceleration, and that would be radial acceleration. Radial acceleration is exactly the same as centripetal acceleration. You'll just find some people use the term radial instead of centripetal. So if you see an A subscript R, that stands for radial acceleration, V squared over R, or omega squared times R. Finally, we have to recognize that radial and centripetal acceleration, so I get one more, I do, okay. Radial and, did I say centripetal? Radial and tangential acceleration are components of linear acceleration. In other words, radial acceleration is measured in meter per second squared, and it's directed toward the center. Tangential is measured in meter per second squared, and it's directed tangentially. These are simply perpendicular components of your linear acceleration, which means that, I'll just draw a new rigid rotating object. Okay, I'm going to say that this thing has an angular acceleration of positive 3 radians per second squared. The number doesn't matter, it's just that it has a positive angular acceleration. That means that a point P on here, and also that doesn't necessarily mean that it's going faster and faster. So I will add that it is in fact omega is positive 2 radians per second. So it actually is going faster and faster and faster. It's speeding up. So I'm not going to draw a vector for velocity. If I just draw the accelerations, here we go. The radial acceleration is toward the center. And I'm now calling that radial instead of centripetal. Remember, I can use either term. The tangential acceleration is tangent, hence the term tangential. The linear acceleration is the vector sum of these two accelerations. So if I plunk this guy up here so I can add them head to tail, the linear acceleration is the vector sum, and that you could put a little L for linear or just write it as A. And so for something that's going faster and faster as it rotates, you're going to find that linear acceleration vector not tangential, not radial, but at an angle. If I get rid of these two, and if I now add the velocity vector, because it's of course tangential, you're going to get that kind of a relationship between the velocity and the acceleration vector. And you say, oh, but they're always perpendicular. The acceleration's always toward the center. That's for something in uniform circular motion. If point P is on a disk that's rotating faster and faster and faster, then your acceleration vector is going to be pointing both toward the center and tangentially. Add up those vectors and you get something like the picture you see here. And I might be able to show you this in our cute little simulation. I'm going to pause this and reset it. And I'm going to, what I'm going to do here is try to manually rotate this thing faster and faster and faster and see if you can that was, I don't know how convincing that was. Pause. Right now it's going at a constant angular velocity, but if I reset, and you can set up the simulation yourself and try it. But can you actually see the acceleration vector not pointing radially, not pointing tangentially, but somewhere in between? It goes. I think you can see it there for a second. Pause. Stop. Well, there you have it. We'll do some problems tomorrow, but that's what I got. Thank you and good night.